So, flux balance analysis is the most important concept when it comes to constraint based modeling. It was one of the first techniques that was used. So, it involves a steady state mass balance, right. What is steady state? There is no accumulation, right. So, whatever substance is coming out, there are some conversions, and at steady state substances are going out, right. So, what would be dx by dt under steady state? It will be equal to 0. The rate of change of rate of accumulation of every metabolite will be 0. Is that right? So, what does that mean? It means that SV equals 0. What does this mean? What is this? What does SV equal to 0 mean? It is a system of linear equations. Is it the moment you have a system of linear equations, you could have an under determined system or an over or an or what you could call an exact system, right. So, this is m equal to r. What does over determined mean? M greater than r, m less than r. So, once again, what is m? Which is the same as the number of equations. Every metabolite has an equation. R number of reactions or fluxes, which is the same as variables or unknowns. So, if I just gave you an equation V1 plus V2 equals 10 and asked you to solve it, how many solutions would you have? Obviously, infinitely many solutions, which is the same thing we can expect for any underdetermined system. So, whenever you have more reactions than metabolites, you will have an underdetermined system or a fat matrix, right. So, when you have an underdetermined system, you now need some other ways of solving it. What happens if you have an exact system? And what is the solution? All zeros. Okay, the right hand side is 0, right. So you know that all zeros is a solution, you know that it is therefore the solution, right. And over determined system, it could be inconsistent, right, or you might be able to fit a good solution, a solution that satisfies most constraints within some epsilon, something like you can do a least square solution and so on, right. So, let us focus mostly on underdetermined systems, which is what we always observe in biological systems or metabolic networks. Right. So, now you have a system SV equal to 0. How do you solve it? So, let us just recap. So, we are looking at a steady state mass balance of SV equal to 0, right, and we want to look at what is V. So, V is the set of fluxes I write it in a horizontal fashion with the transpose to save space on the slide. So, V is nothing but and you can also think of external fluxes, not be an N, it can be an M, right. This is going to be your R cross 1 vector that you are going to find out. This is what multiplies S. What is the size of this vector?
M plus 1.
Right. So, this is going to be M cross R, this is R cross 1, this is M cross 1. Clear? So, we basically discriminate between the internal fluxes and the external fluxes. External fluxes involve exchange with the outer environment. So, you will typically have a cell like this, all these are internal fluxes. And let us say so, think of a cell, you have several internal fluxes, internal reactions. So, these are different metabolites and you can think of all these as internal fluxes, and then you can also have some nutrients coming in, things being secreted outside by the cell, important products and so on. So, these are what we call the exchange fluxes and these are the internal fluxes. And so on. These are not necessarily reactions. So, you could still write them as a reaction. You would just write them as, or essentially A coming in to the cell, and this would just be something like D going out. So, the stoichiometric matrix column corresponding to this would just be -1 and everything else is 0. Sorry, this would actually have been you can also have it as A external giving A and so on, but the easiest way to write it as just A coming in, right. So, then you can balance it with the rest of A, it will become clearer when we look at an example. And then we go ahead and add constraints. What kind of constraints can we add? Stoichiometry is accounted for, right. This is your stoichiometric constraint, right, whereas you can add constraints on reversibility, irreversibility. So, there are irreversible reactions which you will say can go only in one direction. So, you can say 0 less than V less than infinity, in practice not infinity, but a large number, and you have reversible reactions which basically can go in either direction, and you can have exchange fluxes or uptakes that can either be reversible or irreversible. So, you could think of a particular flux being like this, can go in both directions. So, now if you get this value as -30, it means it goes in this direction. You have to commit to an arrow sign in the first place, but once you do that, let us say this is a reversible reaction, and if it now has the value -30, it means it is actually 30 moles per liter per hour going in the opposite direction. So, how do you go about solving this problem now? You have an overdetermined system, which means you have to find out a single solution, if you want to find out a single solution to the problem, you need to come up with some other constraints or some other strategy. How would you go about it? So, if I wanted to solve this this system V1 plus V2 equals 10, one way of potentially solving it is, if I said, told you some other conditions, if I said this makes it a little better, but the problem is still that I have no, I think this almost specifies a solution. Now there is only one possible solution that is possible. So 5 plus 5. Right. Is that clear? So you need to give some other constraints or go in for some optimization. So usually we resort to maximizing something. Let us say solve this subject to max V1, then the answer is very simple, 10, 0. Solve this subject to max V2, 0, 10, right. So, it is easy to solve it, to find potentially a unique solution, not necessarily always, when you start specifying an optimization criterion. So, typically it has been found that if you try to maximize growth or minimize nutrient uptake, they are useful optimizations to carry out to find out what is the possible flux distribution. So, it turns out that maximizing growth is a very useful objective function. You can have different objective functions like minimize nutrient uptake or maximize metabolite production or efficient metabolite channeling and so on. We will look at these a little later, but you basically minimize or maximize some linear combination of the fluxes subject to your stoichiometric mass balance constraints, right. And you can also do perturbation analysis, you can do in silico gene deletion, drug inhibition, so on and so forth. We will see what these are, in a later class. So, let us look at a very simple example, right. So, here you have a reaction coming in like this, A giving B plus ATP, A giving NADH plus B on this direction. So, it is not exactly balanced in that sense, but you can imagine that RA is equal to RB equals x1 plus x2. This is again very similar to something that you have studied in school, this kind of a circuit diagram which splits across Kirchhoff's law. Kirchhoff's law is basically charge balance, here we have mass balance, it is essentially the very same thing. So, here you have constraints, I say x1 greater than 0, x2 greater than 0 and x1 plus x2 equals RA. So, because of that all your solutions lie on this line. Now, you can say maximize x1, which means you will get to this point x1 comma RA comma 0, or you maximize this point, you will get to again RA 0 comma RA as the other point, right. So, here you basically have switching of one production and so on, right. So, in this case the maximization of NADH switches off ATP production and the maximization of ATP switches off NADH production, right. But you can have a whatever appropriate objective function you want.